This is a video on regression analysis and how it might be used in industrial engineering. I'm going to give you a really simple example of a time study and to see if we can glean from the time study data more information about the process given the data. So I have here 11 cycles that I've timed of a certain process. And in column C, I have the observed time in minutes each time that I timed this cycle. And then in B, I also noticed that each cycle had a different batch size. So there was a different number of units that were being processed. And so I want to know if there's anything I can glean from this. So what I'm going to do is I'm going to create a fitted line that has batch size as the X value and observed time as the Y value. So I'm going to go ahead and insert, just the first thing I'm going to do is insert a chart that has, that's a scatter plot. So I can see here that there does seem to be a linear relationship between this. It's not perfect, but there is a linear relationship. So I want to understand that linear relationship. And one way I'm going to do that is I'm going to, I'm going to insert a trend line. So it's a linear trend line. And I can see that there's a line there. I want to know the values of that line. So I'm going to use the line estimate function to give me the coefficients of this. So I have the known y's, which are these, and then I have the known x's, which are these. And so what it's giving me here is this is the slope value, and this is the intercept. So I know here now that the equation is such that the observed time is equal to 5.03 plus 3.20 times the batch size. So that's my equation that I got from these values. And that'll give me a way that I can actually now estimate what the value is. Now, if this 5 minutes, this is actually, it takes 5 minutes no matter how long the batch size is. So I think I'm going to call this, I'm actually going to call this setup time in minutes. So that means that no matter how many units I produce, it's going to take 5 minutes to set it up. And then the slope is going to be the minutes per unit process. So that's how long it takes to process one unit, is about 3 minutes. And that'll give me this value. So now I have a really interesting a model that then I can predict what is the batch size. If I know the batch size, I can predict how long it's going to be. So that's really, really cool. But there's also other things that I might be able to glean from this. One thing that I want to look at is I noticed when I did this, I actually had noticed that the first 5 times I timed it, there was a guy named Joe that was doing it. And then the last 6 times, Joe wasn't there, it was some other person. So I'm defining a variable that's called Joe and not Joe. So that means that if it's 1, that means Joe did it. And if it's 0, it means that Joe didn't do it. So I'm going to use multiple regression now to actually enhance this model a little bit and say that I think there's going to be a relationship between the batch size and the worker that can produce the observed time. Now, the way I'm going to do that is I'm going to use the analysis tool that is in Excel for regression. So I'm showing you how I'm going to get to that. And actually, I'm going to cancel all of that. Oh, sorry. So what I'm going to do is I want to say that I'm going to estimate my Y value is observed time. I've already indicated it here. And my X values are going to be both batch size and the fact that it's Joe and not Joe. And then I have an output range. I'm not going to get the residual plots or the line fit plots. I just want to know what is the data that's coming out of this. So let's go ahead and do this. This is a little bit more, so this is multiple regression where there's 2 data points that are going to predict the outcome variable. So I have down here a summary plot. So let's look at what this tells us. So what this says is that actually this value, the adjusted R-square, is the one that I'm most interested in, because the adjusted R-square accounts for the fact that there are multiple variables in this. Now this is a super good fit, right? 0.99. We know a perfect fit is 1. So this is a great, a really good fit. We also want to look at the fit of the whole model, and we can look at that by the significance of F. So this is a very, very small p-value. This is the p-value that we'd be looking at. So what the p-value tells us is the probability that this is not a good fit. And so what this means is that it's so small that it is a very good fit. The other information I want to know are these values. So this tells me that the intercept, or the setup time, is 15 minutes. The time per unit is 2 minutes and 84 seconds. And Joe actually contributes a -8 minutes. So that means he's slower than the other person I timed by about 8 minutes. So this could allow you to look at, well, what is the impact of the operator? And what we might want to do is use the rating to calculate the normal time in order to then fit that data to it. We also want to look at these values, which are the p-values associated with each of these intercepts. So this is the probability that this value is 0. And you can see these are very small, so they're all significant. So I've just done a more sophisticated model associated with this. So now we can say observed time is equal to 15.36 plus 2.85 times the batch size plus, minus 8.15 times Joe or not Joe. So that lets us know that's now the model I have. It's a more sophisticated model that we can use to predict. So that's a little bit of a look at how you might use regression, multiple regression in industrial engineering.